Hey there, geometry students. I'm so glad that you tuned in today. I'm seeing encouraging things with the view counts on YouTube as far as the duration. So those of you that are checking in or watching for a longer time, that's good. Make sure you keep doing that. I just wanted to encourage you because there are some of you that are really working hard on this, and I'm super proud of the way that some of you are just really stepping up to the challenge. And anybody who's listening right now, I'm proud of you because you're here doing what you need to do today. Good job. The last couple lessons have been hopefully not too terribly difficult for you. This also, we're going to go through pulling apart this formula for the surface areas of pyramids and cones. I'm going to walk you through a couple things on the website for if you want to take a look at some of these things. We can't hold them in our hands, but what you can do is you can take a look at some really good 3D models of these, which might be helpful to you, especially those that are very tactile and you want to play around with some things. So for a while, we're going to just take a trip into the internet, and some of these links are even on Wikipedia. And even though Wikipedia is not like the be-all end-all source for things, sometimes there's some very good things to find on there. So I'll just invite you to come with me in a little while. But right now you can get the idea in your head of what these are. We had talked about pyramids in your past at some point, but a pyramid, once again, has a nice base of a certain shape, and then it comes up to one point that's not on that base, and all of the lines come up there. And so what we end up having is some kind of a basic shape, and then that many triangles going up to make a point up at the top. So today we're talking about surface areas of pyramids and cones, but with the idea that these are all regular pyramids. In other words, the bases are regular polygons, meaning they have all equal sides and equal angles. So those are the specific types of surface areas we'll look at. Now, yesterday we talked about surface areas of prisms and cylinders, and it was the amount of square units it takes to cover them over. So when we look at pyramids and cones, it's how many square inches it would take to cover these surfaces. And notice I have a formula here that we need to pick apart and find out what this really means. S equals L plus B. L, once again, being a lateral surface area, and B being a base. Now the bases are the bottoms. Okay, those are the ones that'll be their unique shapes. It might be a triangle or quad or a square, or a regular pentagon or a regular hexagon, heptagon, octagon, and so on and so forth. This L, lateral surface area, is going to be all of the triangles that go around that make up the sides, if you will, of your pyramid. So it's all of the sides that are not the base. Now in this case, the base is an equilateral triangle, and then the sides are these other triangles. Because this point can stretch up here, the triangles might be taller, or they might be skinnier if you punched it down like that. I think I can do that for you. There we go. Oh, is it going to work? I hope it's going to change it proportionally. Oh well. But anyway, you can have the sizes change on that. So I made mention that there are triangles on the side. These triangles are going to be isosceles triangles because you've got a base, but then these sides are all going to be the exact same length because the base is regular and the point is like right up above it. Okay, so we've got all of these triangles that go around the sides of these pyramids are all equal triangles to each other within their same individual pyramid. So when we are going to look up this formula and we need to find the lateral surface area, we're thinking in terms of the triangles that go around them. Okay, so let's start off by thinking that way. Notice I have this line drawn in each one of them that goes right along the edge. Oh, it's not really an edge. It goes right along one of the faces, but it comes down and makes a right angle. So it's coming down through the middle of one of the sides of the pyramid. Okay, it could have been drawn on this front part, it could have been drawn on the other side. I just drew them where it seemed to make sense so you could see them the best. Those are called the slant height. Okay, if you measured from here to here, that's called the slant height. You're not measuring right along one of the edges. You're measuring that line that goes right through the middle of the triangle that's on the side, to be called the slant height. The reason the slant height is important is because it is the height of one of the triangles that makes up the sides of this pyramid. S, we're going to say, is the length of each side of the base. Okay, even though it can't really be drawn to scale here because you have to draw in 3 dimensions, I'm telling you each one of these sides has the same length. Each one of these sides has the same length. Each one of these sides has the same length, and we're going to call that S for a variable. We're working on getting a formula. You won't have to derive the formula, but I need you to understand what the pieces of the formula are. So just stick with me and listen to the whole thing. This says the area of the triangle. So the area of one of these little triangles is, of course, 1/2 base times height. Base and height. Our base is S, and our height is L. So the area for one of these little triangles is 1/2 slant height times the length of a side of the triangle. N, we're going to say, is the number of sides for the base. So for this one, N would be 5. For this one, N would be 4. For this one, N would be 3 because there are 3 sides here, 4 sides here, and 5 sides here. So we're working with a formula where the L, the lateral surface, is the number of sides times the number of triangle, or times the amount of triangles, the area for the triangle. Number of sides, area of triangle. Because there are this many N triangles, and here's the area of a triangle. So we have 1/2 N number of triangles, S, the length of each side of the base, and L, the slant height. So what that brings us down to, wait, where did P come in? Oh no, P is perimeter, okay? P is perimeter, so think about it. N times S, the number of these pieces times the length of the side is going to give you the perimeter. So our formula for the lateral surface area is 1/2 of the perimeter times the slant height. This part is the formula that you need to write down right here. Okay, we have L is 1/2 of the perimeter times the slant height. We have to still talk about B, because remember, L plus B. So this is the L part of it. The base part of it is the area of the regular polygon that makes up the base. The regular polygon that makes up the base. Now squares are kind of easy to find the area of the base, but the others, a lot of times what you'll be given for this type of problem is the apothem. Okay? And the apothem, if you'll remember correctly, for that part, this is not up in the top of the pyramid right now, this is down in here, goes from the center of that regular polygon right out to the side, right in the middle. It makes a right angle with it, just right along the flat bottom of this. So your base is 1/2 of the apothem times the perimeter. The base is 1/2 of the apothem times the perimeter, because we had already talked about where that formula came from when we were in that section. So what we have now is we have two things to put together. We have our area of our base, and we have the area of the lateral surfaces. So if I put this all together, okay, here's this right here. I'm putting it all together. Make it nice and featured here. Okay, S equals L. Here's our L. And plus B. Here's our B. 1/2. So when we factor this out, we have a half that's in common. You have a P that's in common. So our formula turns out to be the surface area for the pyramid is 1/2 of the perimeter times the slant height plus the apothem. So when you're given these things in a picture, when you're given the slant height and the apothem, you do 1/2 the perimeter of the base times the slant height plus the apothem. All right, so you would be like taking, when you do your assignment, now today I've got this lesson, but your job on Monday is going to be to spend all your time working on the assignment. I'm not expecting you to watch this today and then be able to spend all that time. I want you to take your time, watch this so that it makes sense. Take good notes. And then on Monday, I want you to spend all of your effort on just working your way through applying this formula to the problems and doing your very, very, very best on that. Okay, so Monday is a work day on the assignment. I will want you to log in and fill out a progress report, but Monday you don't have a new lesson. Okay, so here's your formula. The surface area equals 1/2 P plus L, 1/2 P times L plus A. Okay. A cone, if you can imagine it, is when you take this and you give more and more and more and more sides to the bottom, because you're getting a polygon that has more and more and more sides. It starts getting closer and closer and closer to a circle. Okay, so you can imagine that your pyramid, the more sides it gets closer to a circle. So our formula that we just found and spent a long time working to figure out, this is, if you need to just break it down to one slide, this would be the most important slide for doing problems. You're going to do the surface area equals 1/2 the perimeter times L plus A. For a cone, it's really the same formula, but the perimeter is now the circumference, which we already talked about that formula. You know the formula for the circumference of a circle, times L plus R. L plus R. And really, when you think about it, okay, you're looking for surface area. Think about this. You're thinking about this whole thing rotating around, the L plus R rotating around. But then because there's triangles involved, we have a half of it. So that might also help some of you understand where the formula comes from. So on your pictures, on your work that you're supposed to do, you'll find numbers that go in these. The number for here goes in here. The number for here goes in here. And so you've got some things to work with on that. All right, now that being said, you've got your formulas. You'll be able to use them. I hope you understand where those formulas came from, just for your understanding. And we need to look at some other three-dimensional figures. Now, as I said, it would be great if I could put some things in your hand so you could see, but there are some good interactive links. I want to show you where to find them on the website, where to find the links so that you can look at these things a little closer. Okay, so we're going to take a look and talk about the regular polyhedra. Okay, regular polyhedra are solids that have faces that are all polygons. Polygons. But in this case, each of the faces have to be regular as well. In other words, they have to have equal sides and equal angles. So here we have a four-sided polyhedron, because there's 1, 2, 3, and then 1 on the bottom. All of those are equal, so it's regular, and when it has 4 sides, it's called a tetrahedron. I need you to write that down. Make sure that's in your notes. This is a regular tetrahedron. This, also known as a cube, but for our purposes and what you'll need to know for the upcoming quizzes and tests, is that this is a regular hexahedron if we're looking for its very fancy name. Regular because all the sides are squared. Hexa because there are 6 sides to it. 4 around this way and a top and a bottom, so it's a regular hexahedron. The prefixes go with the number of sides. Tetra means 4. That's kind of another one that you won't be familiar with. Hexa, you know, so it's got 6. Octa means 8. So this figure has 8 sides. They happen to be made up of triangles, which is a very interesting thing. But it is a regular octahedron, meaning it has 8 sides to it. You might remember the prefix dodeca meant 12. And icasa you may not have heard of before, but an icosahedron has 20 sides. So what you need to write down is a regular tetrahedron has 4 sides, a regular hexahedron has 6 sides, a regular octahedron has 8 sides, and a regular dodecahedron has 12, and icosahedron has 20. And so if you know the area of just one side of these figures, and you know how many of them there are, the formula for this for surface area is the number of sides times the area of one of the sides. And you would have to be given enough information to find those areas, or maybe they would just give you the area. So for example, if you were told flat out that the area of this triangle is 10, and you had 4 of them, that would be 40. If you were told that the area of one of these faces is 11, and you have 6 of them, then the area would be 66. You're simply multiplying the number of sides times the area. But let's see about this interactive link. Okay, now you've been on this website, and this is how you've been getting your information. Here's our geometry website. You've been here, okay, with all of your instructions there and all the links to click. And in order to get to where you are right now watching this, you would have had to have clicked this. The link is not up yet because I'm still recording it, but you will click this link when it's time, and then you would click the review for it. But along here We have these other things. If you need to look for instructions for prior weeks, you can do that. But right down here we have interactive geometry links, and that's what I want to look at just real quick. Okay, the interactive regular dodecahedron, which means that you can bring that up and hopefully spin it a little bit and take a look at it. Let's take a look at your regular dodecahedron. Like I say, Wikipedia can be good for its purposes. So what I have here is I have a dodecahedron. You remember it's got 12 sides, so we can spin this around and kind of get an idea of what it looks like. You can't hold it, so it's kind of hard to count to make sure they got the sides right. I can spin it though if I want to. That's kind of fun. But you kind of get the idea of what a dodecahedron looks like. This is a net of a dodecahedron. I love this graphic, okay? Because here's what's happening. You have your net, and it shows it actually folding in on itself. And so for this, you can see that you've got all of those sides, 12 sides, 1, 2, 3, 4, 5, 6, and another 6, that makes 12. So there's 12 sides and they're folding all together. And so if you even went to this and clicked on it and you like to cut things out and see it happen, you could even get yourself a piece of paper and cut it out and see it happen. And then it's very easy to understand that if you know the area of one of these little pieces, you multiply it by 12 because there are 12 of them, you're going to get the area of the paper or whatever that was needed to make them. So I love this as a link to be able to talk about a dodecahedron. All right, we're going to navigate away from that a little bit, and I want to take a look at your icosahedron. Icosahedron we know is 20-sided. So we'll take a look at that. Now it doesn't take you right to the link, but there are some over here that are worth looking for. I would like to look at the rotating model of an icosahedron because that's kind of cool to look at. Okay, there it is spinning. Okay, so my icosahedron is made up of all equilateral, equiangular triangles. So there are 20 of them. So since there are 20 of them, you would be able to multiply by 20 if you know the area of one of them. I'm going to go back. And I do encourage you to go click through on those links and kind of do some of these things yourself. The model of the regular icosahedron, I'm not quite sure that I'm convinced that it really is one. But this net folding thing is fantastic. I love these net folding ones because it actually shows the pieces. If I were to pause it, which I'll do in a second, we can actually count them and see that it folds up as we're expecting there to be 20. Let's see if I can get it to pause. Pause, stop. Oh no, it's not going to pause for me. But anyway, we could count this and you could find out that there really are 20 in that. So 1, 2, 3, 4, moving right along. All right, actually, let me see. Can I make it pause? It should be able to pause. It just doesn't seem to want to. It wants to run this graphic, but that's okay. If you stopped and paused it, you could count on the net. You'd find that there are 20. They do roll together and make this wonderful icosahedron. And we put it together, we can figure out how many there are. There were some other things, other links on that. Let me go back. And that might be it. Oh, this one's kind of neat. This one shows it rotating inside of a circle because what we might have noticed that it was almost ball-shaped. As they get more and more sides, they become closer to an actual ball shape. So this one's rotating inside, and that's pretty cool. I like that. And so that brings us through there. Now, here's a thing once again, for those of you that are tactile, that like to touch and hold things, this isn't really for this lesson, but if we go back to previous lessons, there are some printable nets. Okay, so what I mean by that is that if you bring these up, and it's going super slow today on my internet, oh my goodness. But if you click on those links, these are publicly available links that if you want to, you can print them on your printer and actually cut them out and tape them together and make these various different nets so that you can see them. As we go through, I think it might be reasonable to figure out some kind of, I'll figure out something that you can do with these nets that would just be something that would maybe be an extra thing that somebody could do. I'll figure out values and all, but if you go there and you look at the nets, you can take them, you cut them out. The tabs are not really part of it. The tabs are just for you to see, so you have something to attach it with, but the net itself is there. Okay, so you could take this net and fold it up and make your cube or make your octahedron out of it. I'm sorry, hexahedron for a cube. This one is not a regular one, however, it does happen to be a pyramid because it's got this base. So you could do various different ones for those that really like to see and touch and be able to figure things out this way. This one's actually a little better because it has those tabs that you can use to fold and tape it together for you to be able to see. So that's that. They even have a nice cylinder for you to print and fold together if you wanted to. Hexagonal prism, oh, that's kind of fun too. It's a hexagon with both ends. So once again, doesn't really go with this lesson, but I did want to point them out because they're there for you and it would be helpful for you to be able to have access to that. So you would do that by going through, clicking to the website that you've been going on just to see these videos, and then going to the interactive geometry links for that. Just since we're on the website, geometry probably has more tabs than anybody else's. You have your assignment sheets, so you know what your assignments are in advance, even if you're not clicking into GradeLink. The notes is where I've been putting all of the notes for the paper notes. You've got your videos that I've been producing daily. If you need to go back and look at any of the old videos, that would be in that link. Bob Jones University, who has graciously provided some resources for your book that you could go back and watch those videos to help you too if you would like. I have a link that has the instructions and links from prior weeks. So if you, for example, are like, wait a minute, I wanted to actually turn in my old homework that I didn't turn in before, you could go back to a prior week and click one of the prior assignments. You would go through and see that they're there. It might say late assignment on it if it's a really late one, or it might just be there and I've already recorded what we've got so far. And so you can go back and click on some of those. Here we go. Late submission, please give a reason. So you can do that if you want. The only thing is, like the old video evaluations, most of them will come up with a note like this where the form is closed for the prior week. Those were worth extra credit, but if you go back and you click on, go back to the regular geometry part for this week, and you tried to click on something that's old and closed, like the test review feedback, we try to go to that and it's closed. Oh, it's not supposed to say extra credit on that one. That's supposed to say something else. Here we go, yesterday's. or 2 days ago. Here we go. It's closed. And if you have a really good reason, like something happened in your family or something happened with the internet, somebody got sick, um, your dog ate your computer or something like that, please contact me. Let me know what's going on, because I don't know. Otherwise, I can't ask you. I can't see you and look at the look on your face and find out you're sad and talk to you about it. So just please keep in contact and make sure that I know what's going on. Remember, I'm for you. I'm not trying to be against you, but I also do want to encourage you to do what you're supposed to do. This is your education. And so I'm here for you. I want to help you as much as I possibly can, and I want to encourage you to also help yourself. All right, that's done. That's good for today, and we will see you hopefully sooner than later, and we're just praying and praying that everything is going to be fine. And I've been praying for your family members and different people who have been sick, and hope to see you really soon.